In question 15, you're asked to produce a simple tree diagram, if you like a probability tree, to show the outcomes on 3 consecutive days. Now, because probability trees actually take place later, I've drawn this as a simple tree diagram. If you wanted to start it off with a 2/3, 1/3, late and early incident, and you're confident there, please feel free to go ahead. Now, in 15A, I'm asked to calculate the number of times it's late on one day. And one day only by the looks of it. So I go through and flag the number of scenarios here. And I've got a total of 12 over 27, which will give me 4 over 9. So it's using the summary of the event sequences there. In B, late on at least 2 days. Now, what I'm looking for there, I'm looking for a chain that involves late on 2 days. And if I go through and work that out, I'll have a total of 1, 2, 3, 4, 5, 6. So I end up with a total, which is 7. 3, 4, 5. So I end up with 7 once I check it through more thoroughly. 7 over 27. That'll be late on 2 days. Now in the case of C, late on the last day, I go and look for the last day figures, and if I do that, I'll end up with probability late last day. I end up with a total of 9 over 27, which is 1/3. And lastly, D, I have to move that up. D, probability of on time, all 3 days. I can totally ignore this last sequence here. It's late on the first day. And you'll see I've got a total of 1, 2, 3, 4, 5, 6, 7, 8. So 8 over 27 is the probability it's on time all 3 days. Now, when you do the next unit, you'll realise that this is quite cluttered, and we're better to go to a situation where we've only got 2 events. It's on time or late, and I might even start calling that O and not O. A 2/3, 1/3 split, and that would enable a scenario a bit like a coin toss, but a weighted coin toss there, and we'd only end up with a total of 8 events to work through, but 3 chain multiplication.